Okay, we're going to play a game. With your neighbor, I want you to come up with 4 everyday examples, one for each of these categories. The first category, we're not going to define a coordinate system. The acceleration vector is pointing up, by which I mean towards the ceiling. And the object is speeding up. The second category, the acceleration is still pointing towards the ceiling, slowing down. Third category, the acceleration is pointing down towards the floor, speeding up. Last category, acceleration pointing towards the floor, slowing down. With your neighbor, 4 examples, go. Okay. First category, acceleration up, speeding up. Who's got an example? Raise your hand. Yes, sir.
Shooting a rocket.
A rocket. And what's the rocket doing? Blasting off. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Good. Any other example?
A balloon.
A balloon that you've let go and it's... okay, that's so cute. Some kid lost his balloon. Okay. Second case. Acceleration up, slowing down. Who's got an example for me? Back in the back.
Riding a bicycle up a hill.
Riding a bicycle up a hill, steep hill. Okay. Baseball. Which way is the baseball going? Up.
Shooting a rubber band.
Shooting a rubber band. Which direction?
Up.
Up. Okay. I just had 3 examples of things going up. And that's why we're doing this game. Folks, there are 2 vectors that describe motion, the velocity and the acceleration. The velocity is also visual if you have any kind of an imagination. As you're going down the road, you can see this great big long red vector going out your front windshield. The faster you're going, the longer it is. Unless you're in reverse, then it's out your back windshield. You can see it almost. The acceleration vector, not so. Acceleration vector, you have to use your gut. If you're speeding up, it's in the same direction as the velocity. If you're slowing down, it's the opposite direction. Now, if the acceleration vector is up, and I'm slowing down, I'm looking for cases where the velocity vector is down. Now who's got an example?
Parachute.
A parachute. You just open the parachute, okay, and you're slowing down. How many of you done that? Jumped out of a plane with a parachute? Don't do that ever again. Your mother called. Don't. Okay. Any other examples?
Throwing a balloon down.
Throwing a balloon down before it turns around. Pretty sure you mean a helium balloon.
Yeah.
Yeah, okay. Okay, what about this one? You dive into water. Once you hit the water, you're still going down, but you're slowing down, so your acceleration is up. All of these examples have to be of things that are moving down and slowing down. Now, case 3, something that has acceleration down and is speeding up. If it has acceleration down and is speeding up, its velocity vector must also be down. Can you give me an example of that? Any example whatsoever? Can you?
Tripping and falling.
Tripping and falling. An old guy example. Okay, anything that's falling. Anything that's falling is going to be an example. So, falling rock. Okay. What about this case? Acceleration down, but it's slowing down, so that means the velocity vector must be up. This is where all those examples fit that we talked about before. Shooting the rubber band up, throwing the ball up. Okay, so a ball thrown up. Now, yes?
What about terminal velocity?
Oh, Very good question. What about terminal velocity? We can't really discuss terminal velocity without talking about forces, which would be the next part of the class. But in all of our problems that we're going to deal with on the exam and the homework, we're going to use heavy objects like cannonballs and ignore air resistance so that we don't have to deal with terminal velocity until we get to where we actually can understand it with a free body diagram. Thank you. Now, all four of these examples can come from this one demonstration. Okay? Let's look at it. You point at which board I'm doing the motion for before I let go, before I launch it. Okay? Point. Be that up there. As it's going up, before it reaches the top, where would it be? Down there. It's coming back down. Okay? And then I catch it and slow it down. There. And right at the top, the acceleration is what?
0.
Oh, really?
Still negative.
Gotcha. Now let's think about that. Acceleration is how much the velocity is going to change in the next little bit of time. If that pen got to the top, it has to stop to turn around. If it had a speedometer, it would read 0 up there. If the acceleration were also 0, what would happen? It'd just hover. That would be spooky. We'd call the Ghostbusters. Okay? Now, if we use our operational definition for acceleration, it was going up, and then a little bit later, it's going down. I've got to take those vectors, and I've got to put them tail to tail. And then I ask myself, what vector would I have to add to a vector up to get me a vector down? That would be my chain vector. So at the top, my acceleration is down. Down. Okay.